Let's consider now what's called the reaction quotient. This has the exact same form of the equilibrium constant, except the reaction does not have to be at equilibrium to use the reaction quotient. So say if we have this reaction, then the reaction quotient would be, I'll do this in terms of pressures, so I'll use a sub P. So remember, this is a liquid, and so we don't include liquids into the equilibrium constant or the reaction quotient, so it would just be 1 over the reactants. So I'd have the pressure of hydrogen squared times the pressure of oxygen. So that would be the reaction quotient. That's also equal to the equilibrium constant form. So they have the same form, except at equilibrium constant means that we're exactly at equilibrium, but the reaction quotient is used when we are not necessarily at equilibrium. Now we can use the value of the reaction quotient to determine which way the reaction will proceed to achieve equilibrium. Let's consider this example. So we have iodine and chlorine gas to produce iodine chloride. So here's a reaction, and let's calculate the reaction quotient and compare it to the equilibrium constant. So Kp is 81.9 at a particular temperature. So the reaction quotient would be the pressure of ICl squared divided by the pressure of I2 to the first power times the pressure of chlorine to the first power. So this is the reaction quotient. This has the same form as the equilibrium constant. This is in terms of pressure. So let's say we have particular pressures of each species. Let's calculate the reaction quotient. Okay, say we have these pressures for the reaction mixture. Let's calculate the reaction quotient. So Qp is going to be equal to, so the pressure of ICl squared, 0.36 squared, divided by the pressure of iodine, which is 0.12, and the pressure of chlorine, 0.10. So this gives a value of 108 for the reaction quotient. So here we see the reaction quotient is greater than the equilibrium constant. And so if we look at the quotient, if the number is too big, that means the product is too high. The numerator is too big. So that means the product is too high in amount. So that means that since the product is too high in amount to achieve equilibrium, the reaction will have to go backward to increase the reactant amounts and reduce the product amount. If the reaction quotient is less than the equilibrium constant, that means that the reaction amounts are too big. We're dividing by a too big number, so that the reaction will want to go forward to reduce the reactant pressures and increase the product pressure. So the reaction quotient, whether it's greater or less than the equilibrium constant, will tell us which way the reaction will proceed to achieve equilibrium.